Good evening, all. Welcome to today's live discussion session for the NPTEL course Water Supply Engineering. I am Reshma R, PMRF Research Scholar from Hydraulics and Water Resource Engineering Division, Department of Civil Engineering, IIT Madras. I shall share my screen now. Okay, so let's start today's session. First question for today's: which of the following adequately describes the properties of colloidal solid particles? Option A: completely stable, dissolvable, and invisible even under a microscope. Option B: remain in suspension, supported by buoyant and viscous forces in water. Option C: electrically charged and cannot be removed through simple filtration. Option D: all of the above. So, which of the options describe colloidal solid particles? You can type in your message answers in the chat box. So, which of the option represent colloidal solid particles? Okay, so let's see what is the correct option. Correct answer is option C, electrically charged and cannot be removed through simple filtration. So, colloidal particles are the particles that have a electrical charge, that has a charge. Also, the removal of colloidal particles is not achieved by simple filtration. So, let's see how the particles are classified and what is the properties of colloidal solid particles. So typically, colloidal solids are particles that range between 1 nanometer to 1000 nanometer. Since they do not settle under the effect of gravitational force, they are also termed as non-settleable solids. Although they are electrically charged, they do not dissolve in water. Also, the particles are so small, that is 1 to 1000 nanometer range. They will not settle in the water and cannot be removed through simple filtration. These colloidal solid particles can be viewed only through high powered microscopes. So, the various particles in water are classified as dissolved solids, colloidal solids, and suspended solids depending upon the size of the particle. So, depending upon the size of the particle, we have dissolved solid, which is less than 1 nanometer in size, colloidal solids or non-settleable solids, which is 1 to 1000 nanometer in size, and suspended or settleable solids, which is greater than 1000 nanometer in size. Among these, both dissolved solids as well as colloidal solids are electrically charged. In the case of dissolved solids, these electrically charged particles will interact with water and becomes completely stable and hence cannot be separated out as such through filtration. They will never settle in water and they won't be visible even through a high powered microscope. Now, the second category, that is discolloidal solids or non settleable solids, though they are also electrically charged, they do not interact much with water and hence they are not completely stable. So these colloidal solids actually have properties that lies between dissolved solids and suspended solids. The particles are so small that they will not even settle in water. But when it comes to suspended or settleable solids, the particles are large enough to be visible with our naked eyes. And these are kept in suspension by buoyant and viscous forces. And if the water is stagnant or not flowing or in a static condition, then the suspended solids may get settled under the effect of gravitational forces. Also, the removal of suspended solids is possible through simple filtration. So, depending upon the size of the particles in water can be classified into dissolved solids, colloidal solids, and suspended solids. Second question is, the most common approach of removing colloidal particles from water is option A, coagulation, option B, flocculation, option C, combined coagulation and flocculation, option D, none of the above. So please type in your answers in the chat box. So as we saw earlier, the colloidal particles cannot be removed through simple filtration. So which one is the most common approach that is adopted to remove colloidal solid particles from water? Okay, so the correct answer is option C, combined coagulation and flocculation. So earlier we saw the classification of particles depending upon the size, and we saw that colloidal particles cannot be removed through simple filtration. Only the suspended solids, which get settled in case of static or stagnated water, we can remove by simple filtration. So when it comes to colloidal particles, they do not settle by gravity. So the most common approach is to make them into a larger group and then forcefully make them to settle. That process termed as combined coagulation and flocculation, wherein in the coagulation we destabilize the particles and enable them to flocculate. Now, flocculate means to form a group of particle or to grow in size. That is, many colloids, once destabilized, combine together to form flocks which are heavier enough to settle down by the effect of gravity. So, if we consider the diameter of the particle and settling time, we can see that when the diameter of the particle is decreasing to 1 nanometer, that is the colloidal size, it is around 8 days to 200 years that it takes to settle through 1 meter of water. Through a depth of 1 meter, if it has to settle, it will take days to years. So, forcefully we have to make them settle. That process is combined coagulation and flocculation. Now, coming to question number 3. Identify the correct sequence of a typical coagulation and flocculation mechanism. Option A, charge neutralization, sweep coagulation, bridging, patch flocculation. Option B, sweep coagulation, bridging, patch flocculation, charge neutralization. Option C, bridging, patch flocculation, charge neutralization, sweep coagulation. Option D, charge neutralization, sweep coagulation, patch flocculation, bridging. So, which one of the following is the correct sequence of typical coagulation and flocculation mechanism? Okay, so let's see the correct answer. Correct answer is option A, charge neutralization, sweep coagulation, bridging, patch flocculation. So, the mechanism of action typically proceeds like first charge neutralization, then sweep coagulation, bridging, and patch flocculation. So, let's see each one of them. So, first we will see what is coagulation and flocculation theory. So, sorry, coagulation is the process by which stable colloids are destabilized by introducing coagulant or by introducing an artificial or outside component into the water to be treated. The stable colloids are destabilized so as to initiate the formation of microflocs. That process termed as coagulation. Whereas in the case of flocculation, the destabilized colloids from the coagulation stage starts bridging to form larger sized flocks. Initially, they will form microflocks and then several microflocks join together, forming larger flocks heavier enough to settle under gravity. Now, coagulation and flocculation has several mechanisms of action. So, the first one is electrostatic charge reduction through double layer compression or simply charge neutralization. So, this normal double layer graph is the normal state of a colloidal particle. It will have a double layer repulsion as well as van der Waals attraction, which will give a resultant force which is highly repulsive in nature. So, in effect, in the normal state, the colloidal particles will not be sticking together or colloidal particles will not be interacting together. But when we introduce an electrolyte, depending upon the dose of the electrolyte introduced, the second or third graph can be achieved. So if it is intermediate electrolyte dose, the resultant force will be still in the repulsive nature, but it will be reduced when compared to the normal double layer condition. And hence, microfloc formation will start initiated. And if the electrolyte dose is very high, then the double layer repulsion will be completely reduced, and the van der Waals attractive force will override the double layer repulsion, giving a resultant force which is of attractive in nature. So, flock formation or coagulation will be achieved. Now, the second mechanism of action is adsorption and charge neutralization. So, here the charge of the colloidal particles is neutralized. The negative charge of the colloidal particles is neutralized by the adsorption of added coagulant ions. So, the positively charged ions from the added coagulant will be attracted and adsorbed on the surface of the negatively charged colloidal particles, thus forming a neutralized particle without any double layer. So that is the second mechanism of action for coagulation and flocculation. Now the third one is adsorption and interparticle bridging. So if we are adding polymers, if we are adding polymer coagulants, it will get attached to the particle and becomes destabilized particle if it is in the optimum polymer dosage, and these destabilized particles may later on join together to form flocks. Also, the destabilized particles may undergo a secondary adsorption, forming a restabilized particle. But if the polymer dosage is of excess, then these excess polymers will combine with the particle to form stable particle. And many of them may join together to form flock fragments. Here also these flock fragments sometimes undergo secondary adsorption to form restabilized flock fragment. Now the last mechanism of action is entrapment in a precipitate or sweep flock formation. So this is when we are adding a larger amount of coagulant into the water to be treated. Then that coagulant will precipitate out, entrapping the colloids on the way it settles down. So while it is precipitating and settling down, on its way, the colloids are either enmeshed or they get entrapped within these large amount of coagulants. So thus coagulation and flocculation, the mechanisms of action can be seen as charge neutralization, sweep coagulation, bridging, and patch flocculation. Moving on to next question, question number 4. A higher velocity gradient in channel flocculators can be generated by option A, closer spacing of baffles, option B, wider spacing of baffles, option C, short circuiting, option D, all of the above. So how do we achieve higher velocity gradient in channel flocculator? You can type in your answers in the chat box. Okay, let's see what is the correct answer. Correct answer is option A, closer spacing of baffles. Tapered energy flocculation in baffled channels is achieved by varying the spacing. So, if we decrease the spacing of baffles, we can generate higher velocity gradients, whereas if we increase or if we are providing wider spacing of baffles, it will lower the velocity gradient. Next question. Question number 5. Pressure filters are more feasible for application in option A, small factory or plant, option B, swimming pools, option C, cottage industries, option D, all of the above. So, where do we use pressure filters, or where is it feasible to use? I'm not seeing any answers in the chat box. Um, all right, so we'll see what is the correct answer. Correct answer is option B, all of the above. So, pressure filters are generally used in the case of small plants, industries, swimming pools, but not for municipal use. That is not for municipal water supply purposes. So, we have different types of filters for the water treatment systems. It may be classified as gravity filters, pressure filters, depending upon the mode of transport adopted or mode of transport that is used for the filtration process. So the gravity filters are further classified as slow sand filters, rapid gravity filters, and high rate filters, depending upon the rate of filtration. Pressure filters are classified as horizontal pressure filters and vertical pressure filters. Other than these gravity filters and pressure filters, depending upon the media or filter used, we have sand filter, anthracite filter, dual media filter, multimedia filter, diatomaceous earth filters, etc. So, pressure filters are similar to that of rapid sand filters. The difference being that the whole filtering material or filter bed is contained in a closed vessel which is made either of steel or cast iron, and the pressure head will be 30 to 70 meters of water. So the filtering bed or filter bed can be either sand or multimedia. Rate of filtration usually varying from 6 to 15 meter per hour, and they need regular backwashing. Backwashing is the process through which the filters are cleaned. That is, the clogged pores are cleared off by backwashing. And the advantage of pressure filter is that these are very compact. So they can be prefabricated and then shifted to whichever site we require. So these are typically used in small power plants, industries, etc. And where we filter groundwater or high quality surface water which do not require clarification. That's an important point. And in groundwater systems, we particularly use this for removal of iron and manganese along with turbidity. So the figure shows a typical pressure filter, a multimedia pressure filter. So disadvantages of pressure filters are, as mentioned, we cannot use it for, or it is not recommended to use it for municipal water supply treatment plants. This is because of the higher cost that it will induce, as well as operational and maintenance problems. So, according to CPHEEO manual, the disadvantages of a pressure filter are the water is being treated under pressure. So the same will affect feeding, mixing, as well as flocculation of the water to be filtered. And if we are directly supplying water, that is treated water from a pressure filter, there will not be sufficient contact time for after chlorination. So when we are chlorinating the water, we need to provide some contact time to ensure that the chlorination is effectively attained. So that won't be achieved if we are using pressure filter. And another problem is water under filtration and the sand bed are not visible. So when we do the backwashing process, we may not be able to observe the effectiveness. Also, the cleaning, replacement, all these processes are difficult in the case of pressure filters. And another major problem is, since that water is being treated under pressure and the water is under pressure throughout the pressure filter. So when we are suddenly releasing it to the discharge mains, there are chances that the filter bed may be distracted or disturbed violently. So the filter effluent will also get disturbed due to this sand bed disruptions. Okay. So now
So in last slide, would you please explain the second point again? In
regarding the contact time for chlorine.
yes, yes.
Okay, so the cases here, the water is continuously under pressure, and once the uh, like fed in water is treated, it will be automatically pushed out to the discharge main or the delivery point or the outlet pipe. So it won't be possible to maintain detention time for the water or retain the treated water, so that the added chlorine is getting a sufficient contact time. Because chlorine, once it is added, it won't be effective in a fraction of a second. So even we have some guidelines that there should be some amount of chlorine that is left behind after the treatment, entire treatment also, till it reaches the consumer end. So when we are doing filtration through pressure filters, it is difficult to maintain this contact time. So this chlorination is primarily like Primarily, chlorination aids disinfection criteria or disinfection characteristic. So that characteristic will be lost if we are using pressure filters for direct supply. So one option we can adopt is we can take the water from the pressure filter to another storage tank. There we can chlorinate, give sufficient contact time, and then later supply. But then what happens is the cost wise it will be increasing. The cost will be increased. Is it clear?
Yes, it is clear.
Okay. Yeah. So moving on to the next question. Question number 6. That is a problem. So, compute the power transmitted by a circular rapid mixer in kilowatt with a detention time of 20 seconds, a relative velocity gradient of 900 per second if the design flow is 1200 meter cube per hour. Assume dynamic viscosity of water as 8.90 into 10 raised to minus 4 Newton second per meter square. Option A 0.0048 kilowatt. Option B 48 kilowatt. Option C 4.8 into 10 raised to minus 4 kilowatt. Option D 4.8 kilowatt. So I'll give you 2 minutes to solve the problem and then I shall explain how to solve this. So please calculate and type in the answer in the chat box. Okay, so let's see how to solve the problem. So the correct answer is 4.8 kilowatt. Sorry, that's option B. Okay. So it is given that detention time of mixer is 20 seconds. Relative velocity gradient G is equal to 900 per second. Design flow Q is given as 1200 meter cube per hour, which is equal to 0.333 meter cube per second. Dynamic viscosity of water mu is equal to 8.9 into 10 raised to minus 4 Newton second per meter square. So we know that the required volume is Q into T, that is 0.333 into 20, which is equal to 6.66 meter cube is the required volume. And we know that the power transmitted, equation 4, power transmitted by a circular rapid mixer is given by P equal to mu V G square, where G is the, okay, so where G is already given and G and mu are given, and V we had just now calculated. So substituting the values, we get P is equal to 8.9 into 10 raised to minus 4 into 6.66 into 900 square, which is equal to 4.8 kilowatt. So I'll just correct it here. It's option B, 4.8 kilowatt. Okay. So hope that is clear. Moving on to the next question. Question number 7. A typical method of cleaning the slow sand filter bed is option A, backwashing with water under pressure. Option B, compressed air agitation of the sand bed. Option C, scraping the top sand and replacing it with new sand. Option D, all of the above. So which of the method is the typical method adopted for cleaning slow sand filters? Okay, so the correct answer is option C, scraping the top sand and replacing it with new sand. So when we are cleaning slow sand filter, we need to remove the first 20 to 30 mm or 2 to 3 centimeters of the sand, and then we need to replace that thickness with new sand. So when we compare the method of cleaning for slow sand and rapid sand, here we can see that in the case of slow sand filters, for the first 1.5 to 3 centimeter thickness, we'll scrap and remove that particular layer, and this is laborious task, tedious task. It requires time and skill. But in the case of rapid sand filters, it's rather simple, because with or without compressed air agitation, simple backwashing will aid the cleaning of rapid sand filter beds. Okay. So next question is question number 8. Typically, the major filtration mechanism in a multimedia filter is option A, sedimentation. Option B, biological action. Option C, adsorption. Option D, all of the above. So in the case of multimedia filter, which is the major filtration mechanism? Which is the major filtration mechanism in the case of multimedia filters? Okay, so the correct answer is option C, adsorption. So the particles will get adsorbed together. Sorry, will get adsorbed to the filter media, and then even dissolved pollutants from water can be removed by this process through adsorption. So the mechanism of removal in filtration are of different kinds, namely physical straining, sedimentation, adsorption, biological action, absorption, electrolytic action. So the first one is physical straining. So physical straining is the major mechanism. Here, particles larger than the pore size of the filter media will be captured. Second mechanism is sedimentation, where gravity settling is enabled on the surface of filter media. Third one is adsorption. In the case of adsorption, the particles stick on the surface of filter media, and this is a major mechanism, especially in multimedia filters. This process can remove even dissolved particles or dissolved pollutants. Fourth one is biological action. The bacteria grown or caught in the voids of the filter media will decompose the impurities through biological reactions, and these will later on get deposited on the surface of sand, which again absorbs and strain out impurities. So this is actually what is happening in slow sand filters, and that is why we are removing the first 20 to 30 mm thickness when we are cleaning slow sand filters. We are actually cleaning off these biological films that have been formed over the filter bed. And why biological action is possible in the case of slow sand filter is, here the filtration process or the movement of water is very slow, that the biological action is possible to happen. Now the fifth process, absorption. So in the case of absorption, the liquid gets soaked up in the sand grains rather than getting sticked onto the surface of the particles. So it is moving inside into the sand grains. Then the last one is electrolytic action. So here, some charged and polar sand particles may get neutralized oppositely, may actually neutralize the colloidal or suspended particles which is having opposite charge. Okay, hope that is clear till now. So the next question, question number 9. Determine the coagulant dose ensured by adding 4 ml of FeCl3 to 1000 milligram per liter coagulant stock in a 2-liter jar. Option A, 8 milligram per liter. Option B, 4 milligram per liter. Option C, 2 milligram per liter. Option D, 1 milligram per liter. So I'll give you 2 minutes to calculate. It's a simple problem, similar to a problem that is in the lecture videos. Okay, so let's see how to solve the problem. The correct answer is option B. Sorry. Okay, I'll change the thing after showing how to solve. It's 4 milligram per liter. Okay, so let's see how to solve that. Mm, So it's given that the coagulant stock, the concentration is 2000 milligram per liter. So that means 1000 ml of coagulant stock has 2000 milligram of that FeCl3, right? So here 4 ml of coagulant stock means 2000 by 1000 into 4, that is 8 milligram of FeCl3. Correct? Because we were provided that the concentration is 2000 milligram per liter. So for 4 ml it will be 8 milligram. So when we are adding 8 milligram in 2-liter jar, it becomes 4 milligram per liter dose. It is option B. So hope that is clear. Okay. So moving on to the next question, question number 10. Match the appropriate coagulation practices concerning the colloid's volume and alkalinity levels in water. So in the first column we have A, high colloid, low alkalinity. B, high colloid, high alkalinity. C, low colloid, high alkalinity. D, low colloid, low alkalinity. And in column 2, we have 1, add coagulant aids. 2, direct coagulant addition with less concern of overdosing and pH maintenance. 3, add high coagulant dose at high pH or acid to lower pH, or add acid to lower pH and then add coagulant. 4, add alkalinity and coagulant aids. So match the columns appropriately. We have option A, A2, B3, C4, D1. Option B, A2, B3, C1, D4. Option C, A2, B4, C3, D1. And option D, A3, B2, C1, D4. So which is the correct option? Okay, so let's see the correct answer. The correct answer is option B, A2, B3, C1, D4. So the coagulation practices that should be adopted based on colloids and alkalinity levels are as follows. That is, if it is high colloid and low alkalinity, then we can add coagulant without a worry of pH, because low alkalinity or lower pH is better because destabilizing is by charge neutralization. So overdosing problem does not arise because the colloidal surface area is too large. Now, if high colloidal concentration exists with high alkalinity, then either we need to first lower the pH, that is, we need to either add acid, or we need to add larger dose. So if the method adopted will depend upon the economy that we have or the financial um, requirement we have. So if high alkalinity exists, either we need to reduce the alkalinity or reduce the pH first, and then we need to add optimum amount of coagulant, or we have to add more coagulant at a higher alkalinity condition. Now coming to the third condition, that is low colloid concentration with high alkalinity. So in this case, we can destabilize by a higher dosage so that that sweep flock formulation occurs, or we can add bentonite, that is aluminum phyllosilicate clay, to achieve destabilization at a lower dosage. And the fourth state is low colloid concentration and low alkalinity. So this is the most difficult case. So we here actually we need to add alkalinity or colloids, because with both low colloid and low alkalinity, the sweep flock formulation will be difficult. So at low pH, overdosage issue also can happen because the colloidal concentration is very low here. So this is the critical condition, low colloid and low alkalinity. Moving on to question number 11. Consider a circular rapid mixer with a detention time of 20 seconds and relative velocity gradient 900 per second, as we saw earlier in a question. So the design flow is also same, that is 1200 meter cube per hour, and dynamic viscosity of water can be assumed as 8.9 into 10 raised to minus 4 Newton second per meter square. So we are asked to determine the approximate depth of rapid mixer. So earlier we had determined the power generated. Now the power required are generated, but here the question is to determine the depth of rapid mixer. So I'll give you 2 minutes to solve the problem. So please solve the problem and type in the answer in the chat box. Okay, so let's see how to solve the problem. So the correct answer is option B, 1.6 meter. So usually the depth is considered as 1.5 times the diameter of the circular tank. So capital D is taken as 1.5 into small d. So we know that the tank volume is equal to section area into tank depth, right? The cross sectional area into tank depth will give the volume of the tank. So in the previous question, we had calculated the tank volume as 6.66 meter cube, if you remember. That is by multiplying Q and T. So that is equal to pi d square, pi by 4 d square into tank depth, that is 1.5 into d. So rearranging and solving for small d, or the diameter of the circular tank, we get it as 1.056 meter as the diameter of the circular tank. Now, since capital D, or the depth, is taken as 1.5 times small d, capital D is equal to 1.5 into 1.056, which is equal to 1.584 meter, or approximately 1.6 meter. Moving on to the next question. Question number 12. As per MOUD and CPHEEO guidelines, a maximum of 4 slow sand filter beds for an area between 250 to 649 meters square are recommended, based on which a slow sand filter with 5 beds was designed. Determine approximately the minimum volume of water that can be treated in these filter beds while maintaining a flow rate of 0.17 meter per hour. Option A, 3250 million liters per day. Option B, 32.5 mld. Option C, 13650 mld. Option D, 13.65 mld. So again, I'll wait for 2 minutes. Please solve the problem and type it in the chat box. Okay, we'll see how to solve the problem. So the correct option is option B, 13.65 mld. So it's given that the flow rate is to be maintained at 0.175 meter per hour, and it is also mentioned that up to 649 meter square minimum four beds should be provided for an area up to 649 meter square. So since we are taking 5 beds, considering the minimum area, that is 650 into 5, the total area available will be 3250 meters square. So the discharge Q is equal to area into velocity, which is equal to 3250 into 0.175 meter cube per hour, which is equal to 13650 meter cube per day, or 13.65 million liter per day, MLD. Hope that is clear. Moving on to the next
Uh,
question. Yes.
Excuse me. The range is given, I think, 250 to 649.
Yes.
So can we assume any other value in between that range?
No, that particular value is given for 4 sand beds, but in the question it is provided told that it is designed for 5 sand beds.
Hmm.
Right. One second,
Yes.
I'll switch back. Okay. So they're
Hmm.
telling that maximum, if it is four slow sand filter beds, that is to
Hmm.
be used for 250 to 649 meters square, not more than that. But
Yes.
the particular in the particular question, they are used 5 sand beds are used. That means
Hmm.
it has crossed this particular limit, right?
Yes.
So we can
Yes. So,
assume any value above this. That is,
okay.
any value above 649 we can assume. So
Yes.
since we need a minimum volume of water, we are going for minimum
Hmm.
area, right?
Okay. Yes. Okay. Thank you.
So now moving on to the next question. That is question number 13. What is the average filtration rate in a sand filter with an area of 40 meters square that filters an average of 8,000 meter cube water in 45 hours? Option A, 4.45 meter per hour. Option B, 4 meter per hour. Option C, 44 meter per hour. Option D, zero point zero 0.04 meter per hour. So what is the average filtration rate? The area is 40 meter square and it can filter out 8,000 meter cube water in 45 hours. So I'll give 2 minutes time. Everyone please try to solve it. Okay, we'll see how to solve this. So the option correct answer is option A, 4.45 meter per hour. So it's given that the area of sand filter is 40 meters square and it has the ability to filter out 8,000 meter cube in 45 hours. So the average filtration rate will be 8,000 divided by 40 into 45. That is 4.44 meter per hour. Hope that is clear. Moving on to next question. Question number 14. Consider a sand filter with an area of 40 meter square as in the earlier question, which can filter average of 8,000 meter cube water in 45 hours. So here we are asked to determine average net daily outflow from the filter if it is backwashed for 24 minutes at a rate of zero point 0.5 meter per minute. Option A, 4,000 meter cube per day. Option B, 8,000 meter cube per day. Option C, 7,520 meter cube per day. Option D, 3,760 meter cube per day. So please solve this. Okay, let's see how to solve the problem. So the correct answer is option B, 3,760 meter cube per day. So it's given that the area of sand filter is 40 meter square, which can filter out 8,000 meter cube water in 45 hours. And the duration of backwashing is given as 24 minutes at a rate of zero point 0.5 meter per minute. So the quantity of backwash water will be zero point 0.5 into 24 into 40, which is 480 meter cube. So that is the total quantity of backwashed water. Now the net production in 45 hours plus zero point 0.5 hour will be like approximately 2 days. That will be 8,000 minus 480, which is 7,520 meter cube. That is happening in 2 days, approximately 2 days or 45.5 hours. So the net daily outflow will be 7,520 by 2, which is 3,760 meter cube per day. Hope that is clear. Moving on to the 15th question.
That that last part,
Yes, it's
net production of water.
yeah. So what is happening is here. Sorry. Yes. So we know that the capacity is it can filter out 8,000 meter cube, but 480 meter cube is used for backwashing. So the net amount produced will be 8,000 minus 480. Right? Because see, in 45 hours it can produce 8,000 meter cube. And then in 24 minutes, that is approximately half an hour, we are doing the backwashing using this much amount of water. So in that 45.5 hours or approximately 2 days, what we are getting the net production is 8000 minus 480 meter cube. Is that clear?
Yes, it is clear.
Okay. So when it comes to a daily outflow, we just have to divide it by the number of days. Okay. So moving on to the next question, that is question number 15. Which of the following statements is or are correct regarding a clariflocculator? Statement 1. In a clariflocculator, the inner tank serves as a flocculation basin and the outer tank serves as a clarifier. Statement 2. Type 2 settling of flocks is most commonly observed in the clarifier of the clariflocculators. Statement 3. The detention time in the flocculation zone is usually between 10 to 40 minutes, whereas that in the clarifier zone is 1.5 to 4 hours. Option A, statement 2 and 3. Option B, statement 1 and 3. Option C, statement 2. Option D, all statements are true. So which is the correct option? Which all statements are true regarding clariflocculator? So clariflocculator is nothing but a combination of clarifier and flocculator. So the correct answer is all statements are true. That is, clariflocculator is a combination of flocculation and clarification happening in a single tank with inner flocculation basin and outer clarifier. So the deposited sludge is raked to bottom near the central weir and then it is discharged. So since the settling zone is receiving flocculated particles, it will follow type 2 settling. That is flocculant type settling because already the particles are flocculated. So it is type 2 settling. And the detention time in the inner flocculation zone is 10 to 40 minutes and in the outside clarifier is 1.5 to 4 hours. So the figure shows a clariflocculator, that is solids contact flocculator clarifier or clariflocculator. So in the clariflocculator, the water will enter the flocculator, that is the inner chamber, and there flocculation happens or flock formation happens as we saw earlier in a question. The flock formulation happens, that is particle join together, destabilized particles join together and forms flock, and then these heavier particles will settle to the bottom and the liquid flows upward in the clarifier zone, that is outer clarifier zone. There we have a detention time of 1.5 to 4 hours, so it will act as a circular settling basin with sufficient detention time, and the clear water is discharged over a peripheral weir into peripheral launder, and the deposited sludge will be raked at the bottom near the central weir where it is discharged. Now, since the settling zone or the clarifying chamber receives flocculated particles, type 2 settling will happen. So the zones in clariflocculator are as shown in figure. As you can see, here we have the center portion or the inner portion we have the flocculation zone, and the outer side, that is clarifier portion, we have the settling zone. So we have the inlet first happening to the flocculator. The water enters the flocculator. There, the water is gently mixed up, causing flock formation. Then around 40 minutes is given so that the flocks will get settled, and then it is moved to clarifier. So there, sufficient detention time is provided so that all the flocks will be properly settled and will be moved to the sludge zone, whereas the clear water will be taken from the top through the outlet zone. So there are different types of clariflocculators depending upon the driving mechanism. That is, they can be either central driven or end driven, and depending upon the bridge length, it can be half bridge or full bridge. So there's two different classifications for clariflocculators. One is based on the driving mechanism, and the other one is based on the bridge length. So when it comes to the design of clariflocculator, the flocculation basin and sedimentation tank has to be properly designed. So there are separate design criteria for flocculator, clarifier, and the last sludge hopper where the sludge is getting deposited. So these slides are already available in the lecture videos as well. Okay, so there we come to an end for today's live discussion. So if there are any other doubts, we can move to that. I'll stop.
Will you please
Okay.
show question number 1, 3, and 10 again? I missed actually. Just questions.
Okay, question number one.
1, yes.
Yeah, 1 second. Okay, this was question number one. That is, which of the following adequately describes the properties of colloidal solid particles? So we have option A, completely stable, dissolvable, and invisible even under a microscope. Option B, remain in suspension, supported by buoyant and viscous force in water. Option C, electrically charged and cannot be removed through simple filtration. Option D, all of the above. So, which option adequately represent colloidal solid particle? So, the correct answer is option C, that is electrically charged and cannot be removed through simple filtration. So the colloidal particles or non-settlable solids as they are called, since they do not settle under gravity, they typically range between 1 nanometer to 1000 nanometer size, and they are invisible to naked eyes. We need to use a high powered microscope to view them. Though they are electrically charged, they do not get dissolved in water. And since the size is small, they neither get settled under gravity. Also, they are not removable by filtration. So, if we see the different particles in water, depending upon their size, it is classified into three as dissolved solids, colloidal solids, and suspended solids. The first category, that is dissolved solids, is of size less than 1 nanometer, and they get completely mixed with the water and become stable. So it's difficult to settle out them from the water or to view them through a microscope. When it comes to colloidal particles, as we saw earlier, they range between 1 nanometer to 1000 nanometer and are visible through high power microscope but cannot be removed through simple filtration. And the last type, that is suspended or settlable solids, they are actually the larger ones, which is of size greater than 1000 nanometer and will settle out in stagnant or static water, or if given proper detention time, the suspended particles will settle out. And these are visible even with our naked eyes. So that was question number one. Next, which question is
Question number 3.
three? Okay, three. Yeah, three is to identify the correct sequence of a typical coagulation flocculation mechanism. So we have option A, charge neutralization, sweep coagulation, bridging, patch flocculation. Option B, sweep coagulation, bridging, patch flocculation, charge neutralization. Option C, bridging, patch flocculation, charge neutralization, sweep coagulation. Option D, charge neutralization, sweep coagulation, patch flocculation, bridging. The correct answer is option A, charge neutralization, sweep coagulation, bridging, and patch flocculation. So that is the uh, typical coagulation flocculation process. So when you come to the coagulation and flocculation theory, what happens is when we add a coagulant to the water to be treated, the stable colloidal particles gets destabilized and then starts forming microflocks or small groups. And the coagulated water, when subjected to flocculation, results in bridging of the destabilized colloids, later on forming larger flocks heavier enough to get settled under gravity. So that is the basic coagulation flocculation theory. Now, for this to achieve, we have different mechanisms of action starting from electrostatic charge reduction through double layer compression. So under normal condition, this that is the normal double layer will exist around each colloidal particle. That is, they will have a van der Waals attractive force along with the double layer repulsive force acting on them. And under normal condition, the repulsive force will be so much greater that the resultant force will be always of repulsive nature. But when we add electrolytes or coagulants, depending upon the dosage, the resultant force will become lesser repulsive. So when the dosage increases from intermediate to high, the resultant force becomes entirely of attractive nature, and hence the double layer will become completely compressed. That is, the particle will get destabilized. So the next mechanism, that is adsorption and charge neutralization, here what happens is that the positively charged ions of the coagulant will get adsorbed on the negatively charged surface of the colloids, thereby neutralizing the particle, because these negatively charged ions are neutralized by the adsorbed positively charged ions. Then adsorption and interparticle bridging. So if we are adding coagulant as polymers, if it is optimum dosage, these will get attached to the particles forming destabilized particle, and many of them may get attached to each other to form flock particles. Also, these destabilized particles may undergo a secondary adsorption, forming restabilized particle. So this will happen under optimum polymer dosage. But if the dosage is higher, then multiple polymers may get attached to the same particle, forming a stable particle. Some of them may also form flock particle, but will eventually result in flock fragments or rupture of flocks, further leading to secondary adsorption and restabilization. And the last mechanism is the entrapment in a precipitate. What happens here is, here we are adding larger amount of coagulant, heavier dosage we are adding, so that it gets precipitated out, along with which, on the way it gets precipitated and settled, some colloids will be entrapped or enmeshed within that. So without destabilizing itself, these colloidal particles will be swept out. So thus the mechanisms of action are charge neutralization, sweep coagulation, bridging, and patch flocculation. So that was question number 3. One more question was mentioned. Which one was it?
Uh, Question number 10.
10. Okay. Mm, 10. Okay. Question number 10 is actually a match the following question, wherein we have in the first column colloid and alkalinity condition, and in second column the application of coagulant aid. So we need to match them together. So I'm directly going to the explanation. Okay. So the correct option is option B, that is A2, B3, C1, D4. So the general coagulation practices based on colloids and alkalinity levels are like, the first case is high colloid, low alkalinity. That is, sorry. So if the alkalinity is lower, this is a good or optimum condition actually, because when the alkalinity is lower, there is no issue of overdosing and destabilization, because here already the colloid concentration is high, so we need to add more coagulant since the colloidal surface area available is large, and since the low pH is low, it is better because destabilization is by charge neutralization. So lower pH will be aiding charge neutralization. Second case is high colloid concentration and high alkalinity. In such a case, there are two choices. One is to reduce the alkalinity first by adding some sort of acid, and then add the coagulant at required amount. Or the second option is to add larger doses because the alkalinity is high. So when the alkalinity is high, we need more dosage. So these are the two options. So it depends upon the financial status. If we have economic feasibility there, we can use more dosage, or else we should go for adding a particular acid, lowering the alkalinity, and then adding an optimum coagulant. Now, the third stage is that low colloid concentration but high alkalinity. So, here also we have two options. One is to destabilize by using high dosage so that sweep flock formation will happen. When we add high amount of coagulant, the colloids will get entrapped and it gets precipitated. So, sweep flock formation may happen. Or else we need to add strong coagulant aids, that is additional aids we have to add, for example bentonite, aluminium phyllosilicate clay, so that at lower dosage itself we can achieve destabilization. And the fourth stage is like low colloid and low alkalinity. Here it is the most difficult situation because uh, low colloid means we are not allowed to add more concentration of coagulants because it will create overdosage issue. And when it is very low alkalinity, like we need to add, there's like when we are adding a little amount of coagulant itself, it may lead to overdose at low pH. So that uh, fourth state is the most difficult case to handle. Okay, so that is the 10th question. Any other doubts?
No.
Okay, so I'll stop sharing my screen. So if there are any other doubts, um, please ask. Okay, thank you. So I guess there are no other doubts. If so, we can close the sessions for today, and then we'll meet during the next discussion session on next Tuesday.